Hello everyone and welcome to a new Lifehack. This is Patrick and today we will continue what we started the last time. So in the previous Lifehack we talked about post-processing in Fidelity and we created contour plots, isolines. I showed you a little bit how you can manage the different views in Fidelity, and essentially today we will be doing pretty much the same but using just the Python API. So if you are more or less the user who interacts or uses the user interface interactively, then today might not be that interesting for you. However, if you want to automate your workflow in Fidelity, I'm pretty sure I can help you to get started. So what are we going to do? We will again focus on our demo case from the last time, and I will show you a way how you can create contour plots, how you can create a Cartesian plot, and create integrals, all just using the Python API. And we will go through a script that I wrote, and I will talk you through this in about 10 to 15 minutes. Of course, I cannot go too far into the details, but the idea here essentially is to understand the methodology, the procedure that you have to take in order to automate your workflow in Fidelity and to find your way into the Python API. All right, so let's get started. Before we jump into the code, I would like to show you the new doc assistant, which we deliver now with Fidelity 23.1. And in the doc assistant, if you are interested in the manual for the Python API, you can go to Browse All Manuals, and all the way at the bottom, you will find this option right here, Fidelity Python API. And the Python API is essentially being rewritten completely. That is the manual, to be more specific. So what you see here has been essentially written completely new in order to help you to find your way into the Python API. So here you have an overview of the different modules from geometry to meshing to the simulation models. And yeah, just give yourself some time. There are a lot of examples, and that should help you to get you started. So when it comes to coding your post-processing in Fidelity, you have to understand the way the structure is built in the post-processing. And essentially, you have to know the difference between a placeholder, a view, and a scene. You have to understand the difference because you will have to build your code based on this structure. And I'm going to show you what I mean by that by resetting this view more or less. So let me just delete this. So what we have here is what is called a splitter placeholder. That is what you have in every context. So every context consists of a set of splitter placeholder. And in this placeholder, I can create either a new panel or a new view. For instance, now I can create a new 3D view. And in this view, I can now start to do contour plots. I can create probes of all sorts, integrals, and everything here is essentially collected in something that is called a scene. And you will be using this scene to create new probes, for instance. So again, splitter placeholder, you create a view, and in this view, everything you build is going to be contained in a scene. I just wanted to highlight that at the beginning because you will see in the code a lot of views and scenes and all that, and it's important that you know where that comes from. All right, so maybe let's execute the script once so you see what it actually does. So I will just go right here and say run Python script. You can also use, let me see, the Python recorder down here. I usually prefer to use this menu here. It's a little bit faster. So I will just go to my code. I can execute my Python script right here. And what it's doing is it will start the results analysis. It will create a series of planes. It will create integrals and evaluate different values on these planes. It will create a control plot, and at the very end, it also creates a Cartesian plot. Let's just wait until this is finished. And after the script is executed, we have our Cartesian plot on the right-hand side. I will address in a minute what we actually see here. And I forgot to hide the turbo machinery components. Let's also hide the interfaces just to make sure. So now we have our contour plot, we have several integrals, and we have our Cartesian plot. And now I will be going through the script with you and explain the code. So right at the beginning, we import some libraries. Be sure to use the Python interpreter from Fidelity. We showed you how you can use PyCharm and add the Fidelity Python interpreter as the Python executable. We showed that a couple of life hacks ago, so be sure you are set up for this. Then we continue here, and this is why I explained at the beginning the difference between a scene and a view. What I'm doing here is I start from a 3D view and I get the scene. So here I say analysis. I use the analysis module that I imported from Fidelity. I get the scene and I get the view because for certain probe generations, Fidelity prefers that you add a scene and a view. Here what I'm doing is I get my active simulation, which is simulation 1 in my case. So I'm just passing the name of that simulation. And after that, I start the post-processing, providing the name or specifically the active simulation itself and the number of processes. So be sure to know that in Fidelity you can also use 4, 6, 8 cores for the results analysis. If you do not know the arguments that these methods take, you can always, if you have used the Python interpreter from Fidelity, you can always hold Control, press here, and then it takes you to the analysis module, and then you can see all the arguments that this specific method requires. So here I got the scene, I got the simulation, and we started the post-processing. Here I'm essentially defining z and span coordinates. So what I want to do is, maybe let me just get a picture of the machine real quick. 1 second. So this is the radial compressor we are analyzing right now. And what I want to do is I want to have 2 Cartesian planes, one at this coordinate at z is 15 centimeters, and no, I'm sorry, 1.5 centimeters, and I want one z plane here. So we will create 2 planes here and 2 planes on a constant span of 50 and 95%. And those are the values that I'm providing here. And I will be using those values to create a plane afterwards. What I'm collecting here are inputs for the integration. So as I mentioned, let me go back to Fidelity. The objective is to define on these planes specific integrals and evaluate values like static temperature, total pressure, stuff like that. And I can do that in Fidelity, but I need certain inputs for the integration. So I need the name of the variable. I need the integration type. So static quantities like static pressure. I use the integration type scalar area averaged. And for all total quantities, I use absolute weighted mass average. And as you can see, there's a certain distinction between the field name and the weight field name. Be sure to check out the Python manual for that. It's all in there. Essentially what I do is I define the input in order to perform the integration later. You will see I will be using this later. These are just two dictionaries that I use to store the planes. So after I created a plane at a specific coordinate, I will put them in a dictionary where the name or the key essentially is the name of the plane and the value is the plane itself. You do not have to do that. I usually prefer doing that because maybe at some time later I have to access the properties of that plane again, and then it's good to have them stored somewhere. Here I start creating the planes. So here I have a list with 2 planes, and here I iterate over this list and I define a name, and then I call my scene. Remember, I call my scene. You will need this scene to create new probes. So I take the scene and I use the method create cutting plane. And this method, let me just double click on there, needs an origin, a normal, a name, and a type. And here you have the docstring for it. You can either read it here in your editor or in the user manual. So I provide the origin, I provide the normal, and I say for type blade to blade. So Fidelity knows I want to create a blade to blade plane. Here I essentially do the same, but I do not create planes on a constant span, but instead I use certain z coordinates. And the difference here is that I also directly perform or create the integrals on this plane. So first I create the plane, and then for every entry in this list, I perform an integration. So first I create an integral for the static pressure, then for the static temperature, then for the total pressure, and then for the total temperature. And that's what I'm doing here. So I iterate over this list, and for every entry, I call my scene, and I use the method create integral. And this method needs a list of entities. So where is the integration performed? It needs an integration type, a field name, and depending on the sort of integral, it needs different inputs. So if you are not sure about this, like I said, you can always just check out the docstring here via PyCharm or the Python API. I provide my inputs, and here I simply name them. So if you have gotten lost so far, let me just go back to Fidelity. So what we did so far is we created these planes and we created these integrals. That is what we've done so far. Now we create a contour plot and isolines. So again, I call my scene and I create a color contour. I use this method. This method also needs entities and a field name in my case. In my case, I chose to plot the Mach number. I also add isolines for this with the corresponding values for min, max, and the number of lines in order to have matching contours and matching isolines. So let me just zoom in there. I'm sorry for that. So as you can see, the isolines match my contour plot. This is something that you do not have to do. Essentially, what I do is I customize my color map. So here I say I want only stripes. I set the range mode, and I set a certain location for my color map. And the last operation I do is here I create our Cartesian plot. Essentially what I'm showing here is exactly what I did the last time. So I'm intersecting the main blade of my compressor with a cutting plane at constant span, I think at 90%, which creates a line from the intersection, and I use that to create a Cartesian plot and plot the static pressure. That's what this right here is doing. And let me highlight this. There are maybe also other ways to do that. I'm just showing one option. And this is just essentially what I'm doing here is I activate the periodicity in order to get a full 360 degrees representation of my machine. Right. So this is what we've done. Oops, sorry. We created integrals, we created contour plots, and pretty much all we already showed the last time, but using the Python API. If you're interested in these sorts of life hacks or hints, be sure to shoot us an email. If you want the script, it's fine for me. I can share it, but please send us an email to support or info@numeca.de, and then we can provide it for you. So I hope this helped. Have fun playing around with it, and see you in the next life hack.